Bobcats. This is Unit 6 Precal, Pre-AP. This is your pre-assessment video for Unit 3, and your test will be tomorrow. So the first problem we have is a log base 6. X squared plus 2x equals log base 6, 24. Because our logs are the same on each side and we only have one, then they will cancel, and we will end up with a quadratic. X squared plus 2x equals 24. So we'll move the 24 over and subtract 24 and set it equal to 0. Then we can just factor to solve. We would have x plus 6 and x minus 4 equals 0, and our value then for x would be x is either equal to -6 or +4. And then we do have to be really careful with logarithms, because we know we can't have a negative in the log, but if I plug in -6 because I'm going to square it, that is still going to be larger than when I multiply by 2, so will still remain positive. So both of these will work. All right, let's look at number 2. Our natural logs, number 2, work very similar to our log with different bases. Of course, you know a natural log is simply a log with a base of base e, which is approximately 2.7. So that's really the only difference. Again, we have 1 on each side so that we can kind of vision them canceling. We would end up with 16x squared minus 48x. Move the 36 over, minus 36 equals 0. We could go ahead and divide everything by 4 in this case. You could just factor out a 4 out here, and when you do, you would have 4x squared minus 12x minus 9 equals 0. And then in this case, we actually will have to do the quadratic formula. So let's go ahead and take a look at that. We're going to, of course, we know your a value is 4, your b value is -12, and your c value is -9. So we're going to use those values and substitute into the quadratic formula. So our x values will be equal to -b, which would be +12, plus or minus the square root of b squared, which would be -12 squared, minus 4 times a, which is 4, times c, which is -9, all over 2a, which is 2 times 4. It's not a negative, sorry. 2 times 4. So our x values will be 12 plus or minus the square root of the discriminant all over 8. When we calculate the discriminant, we will get 288. We will need to reduce our radical. I'm going to go over here to the side and do that. So 288. You can do it several ways. I'm just going to use the prime factors. Divide by 2 would be 144. Divide by 2 would be 72. Divide by 2 would be 36. Divide by 2 would be 18. Divide by 2 would be 9. Divide by 3 would be 3. And we're looking for pairs. Since it was a square root, there's a pair of 3s, pair of 2s, and another pair of 2s. So we have 2 times 2 times 3. So 2 times 2 is 4 times 3. 4 times 3 would be 12. So all of a sudden, we have now reduced this to x equals 12 plus or minus, and we have 12 square roots of 2 all over 8. And then of course we can make these, reduce these all by 2, or actually all by 4. So we would have x equals 3 plus or minus 3 square roots of 2 all over 2. And you can just leave your answer just like that. Okay, here we are at problem number 3. Again, now we have exponentials. Again, these are 1 to 1, just like our logs a while ago were 1 to 1. They're both base e. Again, that's our natural base e. So we're just going to be solving the exponents here. So we have 3x minus 1 equals 23. We would subtract or add the 1, and we would get 3x equals 24. And then we would divide by 3, and of course now we have x equals 8, which seems to be a good number. All right, let's take a look at number 4. All right, here we are again, natural base e, again 1 to 1, so we're really here solving a quadratic, 2x squared minus 9x. And in this case, we would bring back over the 18 and set it equal to 0. I believe this is one of those that we can factor. I'm going to go ahead and use a little slip and slide method we used before, where you slip the 2 over here and multiply the 18 by 2. So you end up with having x squared minus 9x minus 36. We'll go ahead and factor, and then be really careful because we'll slip the 2 back into our problem in a minute. So let's just look at factoring. We have x and x. Multiply to 36 and add to 9. If we're going to multiply to 36 and add to 9, I believe we're going to get 3 times, let's see, I believe we're going to get 3 and 12. We want the 9 to be negative, so a negative 12, a positive 3. Again, when we divide out or slip the 2 back into our problem, your factors would be x plus 3/2 and x minus 6. So your solutions then would be x is equal to negative 3/2 or positive 6. And again, you have to be a little careful with negatives in logarithms, but not exponents. They're fine as exponents. Let's move on. All right, again, here we have an exponential equation, and we can rewrite this exponential equation to be 1-to-1 property. We could rewrite 1024 as a base 2. So we're going to have 2 to the 3x equals 2, and that would be to the 10th power. If we take it 2 to the 10th, that would give us 1024. So therefore, we have 1-to-1. So now we have 3x equals 10, and therefore x is equal to 10 thirds. And we have that answer, number 6. All right, here again we have factoring. We have some fractional exponents which make it seem like it would be kind of tough, but if you take a look at it and break it down, it's really not that difficult. Again, we have x, it'd be like x squared. If it was x squared, it'd be x and x. If it was x to the 4th, it'd be x squared and x squared, because you would add exponents, and this is 4 thirds. So we're going to try x, and our hint is this middle value, this 2 thirds. I can write this as x to the 2 thirds times x to the 2 thirds. And I can do that because we would have the same base, and you would just add the 2 exponents together, which would give you 4 thirds. Now, I need to look at negative 6 is what I'm really focusing on, because my 2 thirds is already there. I need to multiply to 8 and add to negative 6. I believe I can do that by negative 4 and negative 2. And now we just get to solve both for 0. So I'd move the 4 over, and I would have x to the 2 thirds equal positive 4. And all of a sudden, I can raise the 2 thirds to the 3/2 power on both sides. That will cross out over here. And I would have x is equal to 4 to the 3/2, which is the same as the square root of 4, then raised to the 3rd power. So the square root of 4 would be 2 to the 3rd power, which would leave us with 8. All right, and let's solve the other factor. We have x to the 2 thirds equals 2. Again, I could take this and raise it to the 3/2. And I would have x equals, and that would become the square root of 2 cubed. Since I can't take a square root of 2, I'm nice and careful in my head without a calculator, and we're not going to have any calculator on this test. It would be 2 to the 3/2 power. All right, number 7. We had some of these on that worksheet, so I want you to take a look at it. Because we have a kind of a more complicated exponent here, we're going to break this into 2 bases. We're going to make this into base 3, and again we want to do that because we want this x isolated, so we're going to have base 3 to the 2x times just 3. So I'm going to pull the 3 out front, which would be 3 to the 1st times 3 to the 2x, which would give me 3 to the 2x plus 1 if I were to put it back together. So I'm going to rewrite that. So this is kind of rewritten. 10 to the 3x plus 3 equals 0. All right, the next thing we're going to do is, again, we're going to keep this 3, but we're really going to factor. So we're going to keep the 3 out here, but we really have 3 to the x and 3 to the x. If we have 3 to the x and 3 to the x, then that's going to give me 3 to the 2x. That's also going to allow me to use this 3 to x in the middle. Now I need numbers that I'm going to use 3 and this 3. So I'm going to need numbers that multiply to 3, but add to, the whole thing will add to negative 10 when I FOIL this. So I'm going to, it's basically the only way I get to 3 is 3 and 1. I just need to know this is going to be 3 times 3 would be 9, and if I put a 1 here, I have another 3. So I have 1 and 3, 1 times 3. I need one of these, both of these actually to be negative. And now I have, in the middle, I have 1, negative 1, 3 to the x, and I have negative 9 to the 3x, and that will give me my negative 10 to the 3x. I know that's a little complicated visually to see, so you really want to focus on these. We did several in class. Go back and look at your worksheets. We're going to solve each factor for 0. So I have 3 times 3 to the x equals 1. I would divide by 3, and I have 3 to the x equals 1/3. I could move this back upstairs and make it 3 to the x. Oops, sorry about that. Let me just scratch that out. 3 to the x now equals 3 to the negative 1. Therefore, x is equal to negative 1. On this side, I have 3 to the x equals 3, and the only way for any number to equal itself would be 1. So x equals 1. X equals 1. Well, hopefully you're feeling a little bit more comfortable with this type of problem. Again, I'm going to just set up my factoring. And we have a 4, so we're going to need to get to 3 in a minute. So I'm just going to make this 2 and 2. Let's see if that will help us. I don't know that that's going to help, though, because our 4 is our base. So actually, I'm sorry, it won't be 2. We're not trying to get to 4. We're trying to get to the 2x. So it'll be 4 and 1, and it'll be 4 to the x and 1 to the x. So 4 and 1 give me my, 4 and 4. Sorry, that's my base. I add the exponents. That would be 2x. A base 4x and base 4x, I would multiply those. I would keep the base, add the exponents. What I'm focusing on now is I need to multiply to negative 4 but add to negative 3. Multiply to negative 4 but add to negative 3. I believe I'm going to need a negative 4 and a positive 1. And I believe that will get me my correct. Let's see, I have 1 of these and I have negative 4 of these, so I have negative 3. That works. Solve each one for 0, so I would have 4 to the x equals negative 1. 4 to the x equals negative 1, not going to happen, so I'm going to say no solution. And then I also have 4 to the x equals 4, and that would be, of course, 1. That would be 1. All right, let's take a look at number 9. First of all, we need to try to get our bases to be 1 to 1. The first thing I'm going to do is take this fraction. I'm going to move the 32 upstairs, and when I get 32 to the negative 1, still to the 2x plus 6 equals 8 to the 4 minus 5x. All right, the next thing I'm going to do is I'm going to change 32, and I'm going to change 8 so that they both can share a base and be 1 to 1 property, which would be 2. So I'm going to make this 2 to the 5th, but it's already negative 1, so to the negative 5, still raised to the 2x plus 6. And this is 2 cubed, still raised to the 4 minus 5x. All right, now if I have a power to a power, I just multiply. Be really careful over here that you multiply both. So I would get 2 to the negative 10x, and I'd say minus 30. Minus 30, and that would equal 2, and 3 times 4 is 12, minus 15x. Minus 15x. All right, and now I am 1 to 1, so I can just solve the exponents. I'm going to do that over here. So I have negative 10x minus 30 equals 12 minus 15x. All right, let's move letters to the left. If we move the 15 over, it'd be positive 15x. If I move the 30 over here, it would be positive 30. So let's see what happens. I believe we get 5x equals, and then I have a positive 12 and a positive 30, so that would be 42. And now all of a sudden I divide by 5, and x equals 42/5. And there you go. All right, go Bearcats. Let's move on now to number 10. Oops, back. Went the wrong way. All right, let's look at number 10. Again, we need to change our base, and I believe we can make them both base 2. So 4 itself becomes 2 squared. It's still raised to the 3x plus 6. 8 becomes 2 cubed, and it's still raised to the 4x plus 2. All right, so if we multiply that out, we get 2 to the 6x and plus 12 equals 2 to the 3x plus 6. to the 3x plus 6. And now our bases are 1 to 1, so we're solving 6x plus 12 equals 3x plus 6. Letters to the left, so I would subtract 3x on this side, numbers to the right, I'm going to subtract 12 on this side, and we are cleaning things up. So we get 3x equals negative 6 divided by 3, and x is equal to negative 2. X is equal to negative 2. And that's okay because it was exponential. And we're going to say it, go Bearcats. All right, let's look at number 11. We're going to have 5x minus 1 equals 625. 3 times x minus, or sorry, 1 minus x. 1 minus x. Let's look a little trickier. Okay, we're going to rewrite 625 as base 5, so we're going to have 5x minus 1 equals 5 to the 4th, all raised to the 3, 1 minus x. 1 minus x. All right, so 4 times 3 is 12, so we have 5 to the x minus 1 equals 5 to the 12 times 1 minus x. And so now our bases are 1 to 1. We are solving x minus 1 equals 12 times 1 minus x. And the next thing we're going to do is go ahead and distribute. And we have x minus 1 equals 12 minus 12x. And then we're going to clean things up. Letters to the left, so we're going to add 12x on this side. And numbers to the right, we're going to add 1 on that side. So we end up with 13x equals 13. And we divide by 13, and x is equal to 1. Nifty. That all came out just really good. All right, let's keep going. Okay, Bearcats, let's continue our pre-assessment. We're on problem number 12. When we've got same bases and we're multiplying, we're going to add the exponents, and then of course when we have the same base and we're dividing, we'll subtract. Let's go ahead and combine the top first. Or go ahead and just maybe switch them all to a common denominator of 24. It looks like between the three of them, the denominator would be 24. Let's do that first. It'll make things really easy for us. So we'd have 15, and if we want the denominator to be 24, of course 6 goes into 24 4 times, and 4 times 1 would be 4. And then we have 15 over here, and we have 24. As the denominator, 3 goes in there, 8. Negative 1 times 8 is negative 8. And then over 15 to the 1/24. All right, let's combine the top first. We have a positive 4 to negative 8. So we have 15 to the negative 4 over 24 and 15 to the 1 over 24. And then when we're dividing, we would subtract exponents. If you want to take the smaller exponent from the larger exponent, you would end up with base of 15 at the bottom. So there'd be nothing at the top. 1 would hold its place. And we would be 15. And you would have 1/24, and you would have minus a negative 4/24, which becomes plus a positive, and therefore you have 1 over 15 to the 5/24, and that would be our final answer. All right, let's move on to the next problem. 13. Again, just a manipulation of a lot of exponents. I would go ahead and multiply the top and the bottom by this exponent on the outside. You could combine first and then do that. It's really just a preference. Since there's no x's inside here, we could go ahead and divide first. We can, or we could go ahead and distribute the 2 first, whichever you prefer. Let's go ahead this time and divide out. So we would subtract our x values. Again, negative 6 would come down to the bottom, and it would be x excuse me, squared minus negative 6, so plus 6, so that's x to the 8th in the denominator. For y, the 7 would come down and be 3 minus negative 7. That would make it y to the 10th. And the 4 would come down and subtract from 8, and we would have z to the 4th, leaving nothing at the top, so we'll have 1 hold its place. Of course, everything is still squared. On the second side, we really can't do much, so I'm going to go ahead and just take power to power. If we raise negative 2 to 3, that would be a negative 6, so it would be x to the negative 6, and in the bottom it would be y to the negative 12. Over here, let's go ahead and take care of this 2 is next one. 1 squared, of course, would just be 1. We would have in the denominator 8 to the 2 times 8 is 16. 10, or y, 10 times 2 is 20, and z to the 8th. And then we'd be multiplying by x to the negative 6 over y to the negative 12. All right, well, if we do that, we can just, this is times 1. We also have y to the 20th and y to the negative 12. We could add those two exponents to combine. And when we do, then we would have x to the negative 6 over x to the 16th. We would have positive 20 to negative 12. That would be y to the 8th. And then we have z to the 8th. And then finally, we would subtract our exponents, since x is the same base, and we would be subtracting a negative, so it would be plus a positive, and that would make that 24. So we would have 1 over x to the 24th, y to the 8th, and z to the 8th. And that would be our final answer. Go Bearcats. All right, let's move on. Our next problem is problem 14. All right, so here we're going to notice in the denominator x and y are raised to the 1/4 power, so we're going to separate that out, and we're going to have x to the 5/6 times y to the 1/6 over x to the 1/4 y to the 1/4. It looks like we need a common denominator. It looks like 12 might be a good common denominator for us. So let's make all our powers, our fractions, denominators of 12. So let's say we would have x, and it would be to the 12th. That would be times 2, so 10 at the top. And y, and to 12, and that would be 2, so 2 times 1 is 2, over x, and we would have 12. 4 goes into 12, 3, and so 1 times 3 is 3. And finally, y would also be 3 over 12. And that makes it pretty easy to do. So we're going to do our x's because they have the same base, and we'll do the y's with the same base. And since we're dividing, we will subtract exponents. We're going to take the smaller exponent from the larger. So in the first, in the x case, we would take 3 from 10. That would be 7. So we would have x 7 over 12. And in the second case, we would take the exponent from the bottom. So it puts y at the bottom, 1 over 12. And I think we can just leave it just like that. All right, moving on. Problem 15. We talked about this a little bit in class. If you were in 7th period. In 4th period, we did not talk about it, so I want to walk ourselves through this. I do want to talk a little bit about when you end up with an absolute value bar. Whenever you have an even, so the absolute value bars are going to occur when you have an even root only. So if it's an odd root, you don't have to worry about it. And you extract or remove an odd amount from the radical, from the root. Okay, so let's see what this means. The first thing I'm going to do is going to realize we have the square root of the 4th root, so I can multiply those and get 2 times 8, or 2 times 8, which would be the 8th root. So I really have the 8th root of 256, x to the 12th, y to the 8th, and z to the 16th. All right, and I'm just going to take these separately. I'm going to take the 8th root of 256 and the 8th root of x to the 12th and the 8th root of y to the 8th and the 8th root of z to the 16th. All right, the 8th root of 256 just happens to be 2, so we can pull a 2 out, and that would be an even amount of times, so we won't have any kind of absolute value bar for that. The next one we're going to do is we're going to have 8. The 8th root, and we can have 1 x come out. And if we have 1 x come out, that's an odd amount, so our x is going to end up in absolute value bars. And in a minute, we're going to have stuff left underneath the 8th root. And since you would have 4 left over, we would put x to the 4th underneath. Here we have 8, and 8. We have 8y, so that makes 1 y come out. That would be also an odd amount of y's coming out, so we're going to put an absolute value bar there, and there is nothing to go underneath. And then finally, 8 goes into 16 twice. That's 2 z's coming out, and because we have our z squared coming out, because we have z squared coming out, that's an even amount, so that we would not have any absolute value bars, so z squared. And that would be your answer. That would be your answer. All right, let's look at 16. Similar situation, except it's just a square root, but that's still an even root, so we do have to be concerned about the absolute value bars. So we have the square root of 288. We have the square root of x to the negative 4. I'm not real wild about the negative. We'll see what happens in a minute. We have a square root of y squared, and we have a square root of z to the 6th. So let's take a look here and see what happens. 288, the square root of 288 is actually, let's see, I want to go over and do this. So I would go 288, I'm going to use my little prime factors, divided by 2, which would be 144, divided by 2, which would be 72, divided by 2 is 36, divided by 2 would be 18, divided by 2 would be 9, divided by 3 would be 3. Alright, and so we have a pair of 3s, a pair of 2s, and another pair of 2s. That's a 2, and a 3. We multiply all that together. 2 times 2 is 4 times 3. That would be 12 out of the house, and this little 2 stays home. So we're going to bring 12 out of the house. 12 comes out of the house, and now let's work on our exponents. The square root of x to the negative 2, you could pull out an x to the, x to the negative 4. You can pull out an x to the negative 2, and that's an even amount of odd, or of negative, but still it's an even amount that would come out. 2 of those would come out. The square root, so you're going to pull out 1y. So when you have a square root of a square, you're going to pull out 1, and when you pull out 1y, because it's only 1, we're going to put the absolute value there. And in the z's, you're going to pull out 3 of them, so z cubed. And because, again, it's an odd amount and it's an even root, we're going to make sure that we put absolute value bars there as well. Alright, so what do we have left over? I don't think everything has come out except the 2 that should be underneath there from the 288. Alright, we don't really like negative exponents, so we're going to move this to the downstairs, and when we do, we would have 12 absolute value of y times the absolute value of z cubed, square roots of 2, and it would all be over x to the positive 2. And that would be our final answer. Alright. Finally, number 17, and this is basic simplification. You cannot add or subtract radicals unless they are like terms, and that means that the radicand and part underneath the radical itself would have to be the same for them to be like terms. So let's see if we can make that happen. Let's go over and simplify 240. Remember, we already have negative 4 times whatever we pull out of the house here. Let's figure out what that is. So for 240, we would divide by 2 and get 120. We would divide by 2 and get 60. We would divide by 2 and get 30. We would divide by 2 and get 15. We would divide by 3 and get 5. And those are all prime numbers. Since it's a square root, we're looking for pairs. We have a pair of 2's and another pair of 2's. So 2 times 2 is 4, comes out of the house. This 3 and 5, which would be 15, has to stay back underneath the house. So this would be 4 outside and 15 underneath. Alright, we're going to add to that 6 times whatever we pull out and the square root of whatever's underneath. So let's see how that works. So we would have 375. We could divide by 3, actually, and that would be 125. And then we could divide by 5, and that would be 25. And we could divide by 5, and we could divide by 5. Alright, and so when we do that, we have a pair of 5. So that 5 comes out, but this 3 and 5 make 15 and stays home because they don't have pairs. So 15's back underneath the radical, and a 5 came out. Alright, let's go ahead and clean up a little bit. We have negative 4 times positive 4, that's negative 16, square root of 15, plus we have 6 times 5, which is 30. Square roots of 15. We have a negative 16 and a positive 30, so we have a positive 14 square roots of 15, and that would be my final answer. Alright, go Bearcats. On the next little part, we will graph. Alright, Bearcats, we're going to continue this time with our graphing part. Notice that we have 3 graphs here, all with exponential, all base 5. Remember in all of our base graphs that our parent function for exponentials, we always have that ordered pair at 0, 1 for a base function. And if it's to the 5th power, if we had the parent function for any of these would just be y equals 5 to the x power. And the only difference between this first one is this negative, which would mean we would have a reflection over y for this one, and so it would reflect over y. Our base graph would look something like this. We would have this point, and then let's say we had to the 1st power, that would be way up here at 5, and let's say we had to the -1 power, that would be at 1/5, that'd be way down here, and our parent graph would look something like that. Okay, that would be like our parent graph. Now, let's go ahead and figure out the reflection. The reflection then would just reflect these points, and this point would reflect over here, and all of a sudden your real graph, your new graph, would look something like this. Okay. Our domain would be all values. Our domain would be all values, so negative to positive infinity. Our range, of course, are values greater than 0. It could never reach 0 because this axis is an asymptote, so it would be from 0 to positive infinity, and both with soft brackets. And then finally the asymptote, in this case, it's approaching, the graph is approaching the x-axis, which is y equals 0. Y equals 0. And you're pretty much there. All right, next let's take a look. Same parent function, so we still have that key point that we started with, the same parent points. This time we have a couple of transformations. All right, remember we talked about this before. If you leave it without factoring out the negative, then you have to do an opposite order. So you would actually go to you would kind of ignore the negative for a minute, and you would think go to the right 3 and then reflect. But if you factor out the negative, which I would suggest, you would get 5, you would get a -1, and it would be x plus 3. And then you would go in the right order. So you would actually go do your reflection and then go to the left 3. Do your reflection and then go to the left 3. So let's see if we can take care of that. So our original graph would have looked something like this, parent graph. Alright. Okay, and remember this parent point, remember this is at 0, 1. I hate to mark all of it on there, but this was originally at 0, 1, and then this point, remember, would be at 1, 5. That's where the original parent points are, and that just kind of gives you a little bit of a few points to move around. So if we look at this, we would actually reflect over y, and then you would move to the left 3, and then move to the left 3. So let's do that. We can't reflect over y here, but we could move left 1, 2, 3, and that would put us right here. And here we could reflect over the y, so we're at 1, 5, we would be at -1, 5, and then we would move left 3. So that would put us at -4, 5, -4, 5. And our graph then would look something like this. All right. Again, we've got a domain, a range, and an asymptote. So domain, range, and asymptote. The domain again is negative to positive infinity. Your range again is greater than 0, so from 0 to positive infinity. And your asymptote is again the y-axis, y equals 0. Y equals 0. We do have a couple of intercepts here. Now the problem is our intercept. Over here, our intercept over here, let me make note of that because you're going to need to know that, was of course at 0, 1. Here, we don't know. We know it's less than 1, but we don't know exactly the value. So you're going to write it as an interval. Your intercept would be at 0, and then the interval between 0 and 1. All right, let's take a look at this last one. Actually, you've got this on paper, so I'm just going to kind of verbally tell you that you would first do the x stuff, remember x is selfish and he goes backwards, so x minus 2 would really put me at plus 2. So I would go positive 2, so to the right 2. And then this negative 1 means to go down 1. So I take my points down 1, and that's how I would get to that value. All of a sudden, if I shift down 1, then my asymptote is also going to shift down 1. So again, my asymptote now is going to be y equals negative 1, just in case that comes up. And of course your graph, I'll go ahead and do that. You're going to go ahead and take it right to 1, 2, so 1, 2, and then you're going to go down 1, and that puts your point right there, which is at really 2, 0. So you have an intercept at 2, 0. Intercept at 2, 0. So an X intercept at 2, 0. And then all of a sudden, your graph hasn't reflected this time, so it's going to go up on the right and down toward the asymptote. And it looks like your y-intercept is somewhere between negative 1 and 0. So it looks like between negative 1 and 0. So my y-intercept might be at 0, comma, and then I would put brackets in the interval, somewhere in the interval of 0 to negative 1. Oops. Alright, let's look at the next set of graphs. Alright, this next set of graphs, we're got base e. It's still exponential, so we're still going to have that key point that we always have, but we are exponential. We will have our transformations that we'll look at, but it is a basic graph again, and still with that parent function having that point at 0, 1, and your parent function still looking something like this. Alright, and our transformations, again, this transformation right here would be left 1, and this transformation would be down 1. So we're going to go left 1 with this point and down 1, which means now we have an x-intercept at negative 1, 0, at negative 1, 0. Alright, and this y-intercept would now be at 0, and you took that because you took this point, which is at 1, and then e, which is 2 point something, and you moved it to the left 1, and then you moved it down 1. So when you moved it to the left 1, that gave us our y-intercept at 0. We moved it down 1. That's just going to be e, whichever the value of e was, and of course we subtracted 1. Subtracted 1. Alright, and I see what else we need. Domain and range. Domain, of course, would be all real numbers, negative to positive infinity, and the range would be everything greater. And of course, the range, our asymptote has moved down because we shifted the whole graph down, so our new asymptote is right here. I'm going to put it right here. I'm going to kind of squiggle it so you know it's an asymptote and not something else, and we're approaching that, and so it would be greater than negative 1. So from negative 1 to positive infinity. Alright, let's take a look at the next one. Alright, let's take a look at these log graphs. Both of these have base 10. If it's unwritten, you assume base 10. This graph, of course, would be the parent function, and then it would be shifted down 2. And this one would be shifted to the left 1 and then down, oops, 4. Alright, so let's just take a look at the parent graph again, and then what would happen. Parent log graph, remember, inverse of an exponential graph, so you're going to have one of your key points on the parent function at 1, 0. Since it's base 10, think about that. You're going to think of the inverse of the exponential, so that would be like 10 to the x power, but you would switch your x and your y's. So let's say that we were at 1, and that would be 10. And so now we're going to put the 1 here and the 10 here. So at 10, you would be at 1. So way out here at 10, you would be at 1. And then let's say we put negative 1. Negative 1 would be 1, 1/10, 1/10, and so at -1. So now we're at 1/10, and that would be at -1. So here's what happens to our parent base log graph. That's what our parent base log graph looks like, or approximately looks like. All right, this would just be shifted down 2. That's it. You're just going to shift this down 2. So if this was 1, 0, and you shift it down 1, 2, it is now going to be -2. It's going to be, I'm sorry, it's going to be 1, -2. So this is going to be at 1, -2. And if you take this point, which was at 10, 1, and you shift it down 2, we're going to be at 10, -1. All right, and so your graph is going to end up looking something like this. Go Bearcats. All right, and your domain, oh, this time they flip-flop. Your range would be all real numbers. So your range would be negative to positive infinity. Your domain would be greater than 0, so 0 to positive infinity. And it looks like we have neither an X-intercept or a Y-intercept that's easily found this time. So I think that you're good. Your asymptote, of course, is the y-axis, so your asymptote is x equals 0. X equals 0. And then the intercept, I guess you could find, you would be able to find an x-intercept. An x-intercept is when you make the entire thing equal to 0. So I guess we could do that. You could go over here and you could say log x minus 2 equals 0. So log base 10x equals 2. And you could say 10 to the second power equals x, and therefore x equals 100. And 100 then would be your x-intercept, and your x-intercept then would be at 100, 0. All right, go Bearcats. I'm not going to go through the steps on every single one of these. I think you're getting the idea. I do have the transformations here. I think you can take your parent graph again and do that. So let's move on to the next one, because you do also have them written out for you. All right, for this one, we have ln x minus 1. That's just natural logarithm. Your graph, your parent graph, is still going to be that basic parent graph, and you're still going to have that key point at 1, 0, and your graph is still going to look something like this. And then this graph would get shifted down 1. So it's very, very similar to the one that got shifted down 2 above, but it would only be shifted down 1. In the second graph, though, we've got a couple things going on. Nothing is happening with x. There's nothing happening horizontally, but you are having two things happen vertically. The first one is the negative. The negative is going to mean to reflect over the x. So, in other words, reflect vertically up and down. And then the plus 1 is going to be go up 1. So you're going to take this base graph that we have over here, and we're going to take this point, and we're going to reflect over the x-axis, which you can't do, and you're going to go up 1. Then you're going to take this point that was way out here at 10, 1, and you're going to reflect it over, and then you're going to move it up 1. Oops, sorry. And here you're going to reflect it over and move up 1. So what our graph would look like, it's going to come down and look something similar to that. Something similar. Oh, I drew my parent graph wrong. Sorry. Cross that out. My log parent graph, I think I'm getting too tired. My log parent graph would look like this. So then my reflection, when I reflect over the x-axis, would come up here and move up 1 would be up here. This would reflect and move up 1 up here, and actually my graph would look like this. Sorry about that. You have the right picture on your paper. Sorry about that. So just make sure that you understood that. Now let's take a look at, I think, the last set, and we're just going to talk about the transformations. Okay, for part E, I think we have y equals ln, negative ln, oops, x. And that would simply take a natural logarithm, again, just using your natural logarithm and reflecting it over, this is reflect over, this would be all vertical, so over the y-axis. And then the last one, you have y equals negative ln x plus 2. You do the x stuff first, you would have to go left 2, then reflect over the y-axis. Alright, the last two are just going to be application problems that you need to substitute in. So you just substitute in the data into the formula. We did that the other day, and we had that if you go back and look at your original quiz. Alright, I hope you have a great evening, and go Bearcats!